We finished lesson 6.3 with solving equations. We'll look at solving exponential and logarithmic equations, and we end with an application problem. The first thing we're going to do is look at the steps for solving exponential equations. If you start with an exponential equation, that means you're going to have a base with an exponent. The first thing you want to do is isolate that base. If anything's being added, subtracted, multiplied, or divided to it, move it to the other side. Then we'll convert to a logarithmic form, so we'll do some looping. Finally, we'll need a calculator or our power chart to solve the resulting equation. Here's example A. 75 equals 3 times 10 to the x minus 1 power. This is an exponential equation because we have a variable as the exponent. Step 1, isolate your base. If that parenthesis is being multiplied by 3, we need to get rid of it. So I'm going to divide by 3. 75 divided by 3 is 25. On the right, the 3's cancel, and we're left with 10 to the x minus 1 power. Now we're going to convert to logarithmic. When we convert to logarithmic, we literally start off by writing that prefix log. The base is 10, so that makes our base for the logarithm 10. And then we loop it. We're taking the logarithm of 25, and we set it equal to whatever our exponent is. There's our looping. From here, we have to solve. Now we're at step 3. It says solve either with a calculator or power chart. If your logarithm is base 10, like we have here, this is what we can plug into our calculator. Anything base 10 is what's called a common logarithm, if you remember that from before. And that means you can literally just plug it in. Now it says round your answer to the nearest thousandth. Type in log 25 and you should get 1.398 rounded to the nearest thousandth. And that'll equal x minus 1. Now to get x by itself, just move the negative 1 over by adding it. Voila! X equals 2.398. Our next example is a little trickier. 4 to the 2x plus 3 power equals 64. Again, exponential because we have an exponent. The exponent is that entire thing right there. That means this whole left side is our base. Nothing's being added or subtracted or multiplied or divided to it, so step 1 is already done for us. The base is isolated. Step 2, convert to logarithmic. Again, we just write the prefix log to get started. The base in this equation is the 4. This part right here. That means it's going to be base 4 for our logarithm as well. And then we loop. We're going to take the log of 64, so that we write the same size, and we set it equal to the entire exponent, 2x plus 3. And this is where things get a little trickier. Log base 4 of 64 isn't something we can plug into our calculator. The base 4 function doesn't work for log, it's only base 10. This means we need our power chart. If we think about base 4, not 6, I don't know where 6 came from. 4 to what power equals 64? That's what we're ultimately evaluating with this logarithm. Well, if you remember in your power chart, 4 to the 3rd power is 64. Therefore, 3 is the evaluation of the entire left-hand side. We used our power chart to figure that out. I hope you were able to follow that. Now, to get x by itself, if we subtract 3, we actually get 0 on that left-hand side. And if we divide both sides by 2, we get x equals 0. That's what solves that exponential equation. Again, you'll either use your calculator if it's base 10, or you have to apply your power chart if it's a different number base. The second part of our solving section starts off with logarithms. The step process for this is a little bit different. If you're given a logarithmic equation, you'll know it because it'll either have the log or the ln prefix. When solving logarithmic equations, the process is similar, but we do have a key difference at the end. Step 1, you want to isolate whatever term has the logarithm or ln associated with it. And then you'll loop to convert it to its exponential counterpart. Again, use a calculator or your power chart to solve. Here's what makes logarithms different. Logarithms have some defining characteristics that we identified in the previous lesson. We have to check for what's called extraneous solutions, and I'll show you what that looks like in our step 4. Example C, log base 6 of x plus 5 equals 3. Notice log base 6 of x is your logarithmic term. That means that plus 5 is after. What we would do first is move that over. I'm going to subtract 5 on the left and subtract 5 on the right. That means we'd have log base 6 of x on the left equals negative 2 on the right. Now that the logarithm is isolated, we want to convert to exponential. This is where we need our base. This is log base 6. That means I'm going to start with a base of 6 for my exponential. And now when I loop it, that's going to give me the actual exponent. And then loop it back, and that's what it equals. So this one wasn't too bad to solve. 6 to the negative 2 equals x. When you have a negative exponent, we make it positive by taking the reciprocal of the base. 1 over 6 squared would be 1 over 36. And that's the value for x that makes that logarithm true. Now, when we check it for extraneous, we want to make sure that the logarithm is still possible. If we plug x back in, log base 6 of 1/36, the key here is this has to be a positive value. And we can take log base 6 of that fraction. That'll work. Therefore, it is a valid option. What kind of answers would not be valid? Well, if you plug x back in and the logarithm becomes negative, then we're out of luck. All right, let's try the next one. ln of 2x plus 3 equals 4. Now remember, ln was that unique base e. And now because the 2x plus 3 is in parentheses, the entire left-hand side is your logarithmic term. So the whole thing is an ln term. Therefore, nothing gets moved over. We'll convert to exponential. If there's no base written for ln, remember it's always base e. That's why we never write it in for ln, because it's always base e. We'll start there, e, and then we'll raise it to the 4th power. And it'll equal the entire parenthesis, 2x plus 3. Well, e to the 4th power won't be on our power chart, so this is going to be a calculator option. Find that e button on your calculator and raise it to the 4th power. Remember, we round to the nearest thousandth. E to the 4th power is approximately 54.598. Equals 2x plus 3. To get x by itself, I'm going to subtract 3. And that gives me 51.598 is equal to 2x. Finally, to get x by itself, I'll divide both sides by 2. And we get x is approximately 25.799. To check it, we want to make sure that when we plug it back in, our output is positive and possible. ln, if we take 2 times 25.799 plus 3, that would become ln of that 54.598. And we can take ln of that number because it's positive. So this number checks out as well. Here's an application problem. The seismic energy X in joules can be estimated based on the magnitude m of an earthquake by using the formula x equals 10 to the 1.5 m plus 12 power. Currently, this would be an exponential equation. Okay, what is the magnitude of an earthquake with a seismic energy of 4.2 times 10 to the 20th joules? Oh boy. They're giving us the x value, and we want to figure out what would the magnitude of this earthquake be. If we know the formula, x equals 10 to the 1.5 m plus 12 power, and they gave us x, we're going to substitute all of that in on that left-hand side. 4.2 times 10 to the 20th equals 10 to the 1.5 m plus 12 power. Notice we have exponents on both sides, but be careful here. The exponential part of the equation that we're trying to solve is wherever our variable is. That means the right-hand side is our exponential part. The left-hand side is all one term. So just something to think about there. All right, getting back to that right-hand side. 10 to the 1.5 m plus 12 power. If we're solving an exponential equation, step 1 is to isolate the base. And notice that 1.5 m plus 12 is the entire exponent. I'm not moving anything over. So then we're going to convert to logarithmic, and we start just with the prefix log. The base is 10, so I'm going to write that sub 10. What are we taking the base of? That big term on the left-hand side. 4.2 times 10 to the 20th. Make sure to put that in parentheses. What will it equal? The exponent on the right. 1.5 m plus 12. Now, this is going to be calculator friendly. Whew! With base 10, we should be able to plug that all in. Please do that now. Plug that into your calculator and we'll round to the nearest thousandth. When you plug that in, you should get approximately 20.623. On the right-hand side, 1.5 m plus 12. If we subtract 12, we would get 8.623 equals 1.5 m. Divide both sides by 1.5, and this should give us the approximate magnitude of that earthquake. 8.623 divided by 1.5 would be 5.749. I'd say that's right probably about in the middle of the magnitudes for earthquakes. And there's your lesson for 6.3. Complete your notes and then start the 6.3 Pearson assignment.